As we continue our discussion about Monte Carlo simulations, let's go through a number of common distribution functions. And since we're doing this in Python, we might as well practice creating these distributions in Python and getting to know the code. So let's start with the uniform distribution. A uniform distribution is where you have a minimum and a maximum, and all numbers in between have an equal likelihood of being selected. So it's a flat distribution. And so when you do uniform in Python, you are going to specify the minimum and the maximum. So I'm just going to put us here. We are here under these chapter 10 simulations. So you can find this at drstephpowers.github.io/BIA. And we are working here in the workbook called Simulation. And when you click on that, you will need to open it in Google Colab, which is the button that appears right here, up in Colab. Log in, save a copy, and then you can edit and run it as much as you want. All right, we're going to actually start here with this distribution section. In our next video, we'll come back to this interest coverage ratio. So let's go into the one I'm logged into. And we need to create some distributions and get familiar with what they look like. So let's import numpy as NP, and we're going to, from numpy, import random. Because when we do our Monte Carlo simulations, as we discussed in our previous video, is that one of the steps is we're going to select a distribution and then randomly generate values from that distribution for the variable we're uncertain about. So that's why we need to be familiar with distributions and be able to randomly generate some data. So we're going to import numpy as NP, and from numpy import random. This allows us to do our random generation. And then because here we're going to graph these distribution functions so we can get used to what they look like, we're going to import matplotlib.pyplot as PLT, and we're going to import seaborn as SNS. Okay, so let's do that. And let's start with our random generation from a uniform distribution. So the first number is the minimum, the second number is the maximum, and the third number is how many numbers you want it to randomly generate. So we could say x is equal to random.uniform between 2 and 10, give me 10,000 numbers. And then I can plot using seaborn, so SNS, and we're creating what's called a hist plot here. We're creating a histogram to represent this distribution, and we'll just do plt.show, so that's where these two packages come in here. And so you can see here that here's the data. There's an equal likelihood, equal probability that the number is going to be between 2 and 10. So see how it's essentially, of those 10,000 data points, there's essentially an equal number of all the numbers in between 2 and 10. And this is a histogram. It's assuming continuous data. So that means it can be not just integers, but it is a float. It is fractions. So 2.5, 2.7, 2.2. And this is a histogram, so it is binning, is putting in a bin. Here, 2 and 2/3, 2 and 1/3, and 2 and 2/3. And that is the number that are falling in between. So this distribution assumes continuous data, equal probability between 2 and 10. Okay. All right. Another distribution to look at is the normal distribution, which hopefully you are familiar with in all your work. The normal distribution has an average we call mu. So it's a measure of central tendency, something that's the average. And then we have sigma, that's the standard deviation. That's how far it's going to range from that average. The numbers here are continuous, so we can have fractions. The idea here is that numbers become less and less likely the further we are away from the average. A normal distribution says that here we have the center, and then it is equally likely that you are on one tail or the other. Now, if you don't know the standard deviation, so you know your data has kind of a central tendency, an average, but you're really not quite sure what the standard deviation is, you can actually estimate the standard deviation. And to estimate the standard deviation, what we typically do is take the maximum, subtract the minimum, and divide by 6. That's because with the normal distribution, 99.7% of the data falls within 3 standard deviations either direction. So if we take the minimum and the maximum, find the range, so max minus min, and then divide that by 6, it'll tell you what that general standard deviation is. So let's go and see how we would do that in Python. To generate data from a normal distribution in Python, we do random.normal. Here we have an average of 100. Here we have a standard deviation of 10. We're going to have it generate 10,000 data points, just so we can look at the distribution on a histogram. So using Seaborn, so SNS.histplot, we will then plot that graph. And what we can see here is here's the average at 100. And then you have 3 standard deviations this direction. 1, 2, 3. 3 standard deviations this way. 1, 2, 3 covers 99.7% of the data. Recall the empirical rule that you discussed in statistics. All right, next distribution. Our next distribution is the log normal. This distribution is similar to the normal distribution, so it's going to be a continuous variable. All these are continuous so far, with a central tendency. But the difference between a log normal and a normal is if you cannot have negative numbers. So if we, for example, are looking at growth rates, we're looking at rates of return, we're looking at ratios, you can't have a negative number, then you use a log normal. So it still has a measure of central tendency, it still has that equal probability in either direction, still continuous data, but if you can't have negative, then we do a log normal. So let's take a look at a log normal. To generate data from a log normal, we do random.logNormal, okay? And when we do a log normal, we have mu and sigma, so we still have the average and the standard deviation. So let's do an average of 5, a standard deviation of 1, and generate 10,000 points. Okay. So here with the log normal, see how it cuts at 0? So even though our average really is here at 5, because it can't have zeros, you can see how it looks different than a normal distribution. Okay, so where average is 5, our standard deviation is 1, but it cuts it so that you can't go below 0. Log normals, as we said, are typically used for growth rates, returns, ratios, percentages. So let's look at a log normal here where the average is 10%. The standard deviation is 5%. We're going to generate 10,000 data points. Plot it with a histogram. And so what you see here is that we have our growth rate here of 1.1 because that's a 10% growth rate. So we have the number and we're growing it by 10%. And then it's 5% standard deviation, 3 directions, covers most of your data. So if you go 15% either way, then you have covered your data. Right, that's why we end up here at 0.95 and 1.25 is most of the data. So it's going to put it here at 1 plus whatever your growth rate is as that center. All right, next one here. Just so before we do that, just a comparison, if you try to do a normal distribution with percentages, so if you just do normal instead of log normal, then what we get here is here's the average of 10% and the 5% when we do that. Okay. What we'll get here is we'll get these negatives. So you have to ask yourself whether or not you can have that negative growth and how you're going to represent that. And so here it would be represented as a negative number, whereas here it is growth, and so it's off of that 100%. We're adding to the 100% or down from the 100%. Okay, so you can choose to represent something as normal or log normal. All of the examples so far have been continuous. That is, you could have fractions. The next one is not. And this is where I've spent a lot of my time. My dissertation for my stats PhD was in Poisson distribution. So Poisson is kind of my favorite. But the Poisson distribution is when you have counts. So we have discrete data. So when it comes to Poisson, we have a lambda, and this is the typical number of events that occur in some kind of fixed time interval. That's what your lambda is. And in our enterprise analytics, we do some inventory management. And I think I have a video there to show you how you use the Poisson distribution for, say, inventory management. Because again, we're looking at counts. And if we are counting the number of products, how many we're going to have on hand, we'll use the Poisson distribution. So some of the application of different distributions here. All right, so Poisson is discrete. It is counts. Fractions are not possible. So if you are counting the number of events, maybe you're counting how many trees grow, how many rabbits you see, we use random.Poisson. And here, the most common number of counts in the period is 8. Generate 10,000 data points. Create our histogram. Our histogram shows, see that highest number there is happening at 8. And you can see that we have discrete because the bars don't touch each other. So you can have 5, but you can't have 5.4. And you can have 6 and 7. And we can have 8. Okay, so Poisson distribution. The last one we're going to look at here is the beta distribution. And this is a distribution that can take on lots of different shapes depending on what you put for that alpha and beta. Okay, so we have alpha and beta are the two values here. The mode, the most common number, is going to be equivalent to alpha minus 1 divided by alpha plus beta minus 2. So this formula here is going to be the mode, and the average is going to be alpha divided by alpha plus beta. So we're going to use that, and we'll look at that just a moment in our Python code. But we can keep these calculations, these average and the mode, to help us figure out what that alpha and beta should be. Typically, we use beta when we have proportions, percentages, or probabilities. So we want the value to be between 0 and 1. Okay. So we can use the beta distribution instead of log normal. Log normal, yes, is growth rates, returns, and ratios. The beta distribution, probabilities, proportions, percentages. Okay. So some options here for how you represent your data. All right, let's go into our simulation. So here's an example of a beta 0.5, 0.5. So alpha 0.5, beta of 0.5, generate 10,000. So notice in this scenario that the most common the most common responses here are 0 and 1. So if alpha and beta are equal, then the two tails are the most popular, and then something in between is much less likely. Okay, let's look at the scenario here where alpha and beta are equal, but they're equal to numbers like 2 and 2, as opposed to fractions like half and a half. So start playing with different values of alpha and beta to see what the distributions look like. So notice here, when we have that alpha and beta are both 2, it starts to look more like the normal distribution, but it doesn't have tails. So notice here it cuts at 0 and 1. So this allows us to use beta distributions for probabilities, where, for example, here the most common probability is 50%, but notice it bounds it at 0 and 1, so you can't have anything that's negative or have more than 100%. And so there we have that beta 2-2 distribution. And so what you can do is you can go back and you can check this alpha minus 1, alpha plus beta minus 2 to see where it puts the mode, and alpha divided by alpha plus beta to see where it puts the average as you are figuring out what beta distribution. Here's one where alpha is small and beta is bigger, so twice the size. If we look at that, what you'll see here is that we can use a beta distribution to show a skewed distribution. So you see it has a small number of data points that are at a higher level, but it's shifted over. So it has this tail here. Again, it's going to be bound between 0 and 100%, but we don't have to have it so that it's like this, where it is equal and symmetrical on both sides. We can have it shifted to one side. That's this one here with a 2, 4. We can shift it to the other side by switching it. So we'll make alpha bigger and beta smaller. And so you can see the distribution here. So we need to choose a distribution that is relevant to the variable where we are uncertain.